Okay, we have an assortment of problems where we're going to look at the types of different types of cases where we have non-differentiability. And for number 11, what we see is that we have a piecewise defined function. And generally this means we're going to be looking at like either a jump or a hole. This one, if we look at the graph of the inverse tangent of x, the graph of that generally looks like this. Right? If we have an asymptote here and an asymptote here, right, we would have negative pi over 2, positive pi over 2, right, and we'd have asymptotes going, let's see, it would be going this way, and it would go through the origin, but but in this case it's piecewise defined, so it's not going to go through the origin. In our case, we're going to actually make it come up, go to its asymptote. At the point when x is equal to 0, right, we're given the point that the y is 1. Right, so this is what the graph's going to look like. Right, and so this one, since it's not continuous, right, this one would be considered discontinuity. For the remaining ones, we're going to look at just kind of like the most unusual terms. 12, right, if we have an odd power on the bottom, an even number on top, it generally gives us this shape which kind of looks like a bird, right? Right. So it comes in positive and it goes out it comes in along positive values and it goes out along negative values. Here we have the case where the slope on this side is negative infinity, the slope on the other side is positive infinity. This one is a cusp. Right. On 13, we're going to look at, so the x is not an issue and neither is the plus 2. So really we're worried about like what's going to happen when you have this term, right? If it's square root of x squared, right, then the graph of this, right, so normally the graph of root x starts at 0. This is actually going to give us something that looks like the absolute value function, right? Because you can plug in and make an xy table. Basically, negative 2 positive squared is negative 2 squared, and then square root is going to give you 2. So it actually mimics the absolute value function. This is considered a corner because the slope on the left side is negative 1 and the slope on the right side is positive 1. Right? And this will carry over to our example where it's x plus root x squared plus 2. Like the x and the x squared won't really affect the differentiability. In 14, right, the unusual term here is going to be the minus cube root of x, right? And this is the same as negative x to the 1/3, right? And when we graph x to the 1/3 power, we end up with, looks like this. Right, so we have a vertical, yikes, this is not working that well. Here we have a vertical tangent. Right, as we pass through 0, right, it becomes vertical. And then 15, right, absolute value, again, is a corner. Right, it gives you the same as number 13. And then number 16, right, we have, we know that x to the 1/3 looks like what we had in number 14 flipped. But then we throw an absolute value on the inside. We're never going to get the negative values from, so x to the 1/3 has this shape, right, where it gave us a vertical tangent, right? But we would never get these negative values, right? It turns into absolute value to the 1/3, right? This would turn into another bird shape, right? And in this case, right, we would get another cusp.